speaker is Rasmus Kyng, who is currently postdoctoral scholar at Harvard. And he will be telling us about matrix martingales and their applications to problems in randomized linear algebra.
Yeah. Thanks for the introduction, Joel, and thank you to the organizers for inviting me. And I guess I should plug this in. So my hope is to look at a particular example of using matrix martingales in numerical linear algebra. Let's see if this is coming on. And try to convince you that you should probably do that too, because it seems to be a really good tool. Okay, so let's start with just concentration of scalar random variables, not matrices. We've got random x, that's a sum of little xi random variables that are each real valued, they're independent, and let's say they have mean 0. And then we ask, is this approximately 0 with high probability? Right, so Bernstein's inequality will give us some concrete conditions under which this is true. So this says that, okay, if it's also always true that our random variable is absolutely bounded, so absolute value bounded by r, and the variance of all these values, all these little random variables summed together is at most sigma squared, then we get a probability that a bound saying that the sum of these guys, x, is probably not larger than epsilon in absolute value with some good probability for large enough epsilon. So for example, I just picked some parameter values. If epsilon is a half and r and sigma squared are both like 1 over log tau, we'll get a probability bound of tau. It's not important that you parse that right now. It's just to give you a vague sense of, you choose some parameters, you get some probability bound. Okay. Now, I said I was going to talk about martingales. I'll talk about matrix martingales particularly. But first, let's just remember what's a martingale. Maybe it's been a while since you used one. So we've got a random x. This is the setup from before. The important things were it was a sum of things. The things were independent, and they had 0 mean. This is not a very flexible set of conditions. Like if I'm doing algorithms, usually my things are quickly not independent. Okay, so martingales, give you a situation where you can deal with proving concentration even when things are not independent. But you need the second condition to be changed. So you ask for something a bit stronger here, namely that not only are your individual variables 0 mean, but you put some order on them from x1 through xk, and you say that xi is mean 0, conditional on any set of outcomes for the previous variables. So it still means 0, no matter what happened before. So I'm going to write that, summarize it as xi conditional on the previous steps is mean 0. Okay, so let's remember Bernstein's inequality and see if we can get the same kind of thing for martingales. We can, and it's then called Friedmann's inequality. This is at least one way to get a martingale concentration bound. So again, we switch from independence to asking for a 0 mean condition. Now, we want to prove a probability bound like this, okay? So I think many of us in the audience here have used probability bounds, so this is yet another one, but you probably haven't seen this one, so we'll be a little bit careful about understanding it. It gets a little bit more complicated in the conditions now, because we don't get to just say that the variance measured by summing up the individual xi and squaring them is small. We get a different variance object that we need to control. So we want to say that the sum over xi squared, conditional on previous steps, this sum is small. Okay? This is harder to do because this is now a random variable, this variance object for xi, that depends on what the previous outcomes were. It's not independent from it, and we need to bound the sum anyway. Okay, but maybe that's a lot to ask for. So Friedmann gives us a little bit of extra flexibility. It says you don't always need to bound this. You just need to bound it with a good probability. Okay, so if it's usually the case that the variance object, in the natural definition for martingales, which was this thing, if it's usually the case that this thing is small, you'll get a probability bound. Okay, so you get a different random variable that acts like a variance, and you have to say this is usually well behaved, and then things will go through. So if this has a low probability of being greater than some threshold sigma squared, my variance, then I'll get the Bernstein probability bound, except for a little fudge of an extra delta probability. Okay? So this is what martingales do for you. They say you can basically pretend that you're doing Bernstein if you can control this funny variance. Okay. So that was Friedman's inequality. But to make it exciting, we need matrices. So there's a matrix Bernstein inequality, which is it's due to Trop, sitting right here, Joel.
And Oliveira.
And Oliveira, sorry, yes, there are different versions. So this is just Bernstein, the concentration inequality that we saw, but sort of adapted to a matrix case. So now your random variable, x, is a d by d symmetric matrix in this setting that I'm considering. Sum over xi, so it's a sum of little xi's that are also d by d symmetric matrices. The xi are independent, they're mean zero. Their spectral norm is always small. And this variance object here has small spectral norm also. And then we get, with like the same symbols down here, exactly the same kind of probability statement saying that the thing is probably concentrated. Like it's unlikely that the sum has spectral norm greater than 0. There are some important changes. We got a d here, which is the dimension of the matrices. So the probabilities get a bit worse. This is basically because we need to union bound over d different eigenvalues that can go wrong. Something like that. The other thing that you should be careful with is that this is a funny way of measuring variance. Okay? Each xi squared is a matrix. We're taking expectations of some funny matrices, we're adding them all up together, and then we're taking a norm. This is going to be extremely important that we have a funny notion of variance for applications. So can we get a matrix Friedman? The answer is yes. And we're just making all the same changes as we did in the scalar case. So we get 0 mean conditional on previous steps. We get this variance conditional on previous steps has to usually be small. Here are some parameter examples. The only thing that changed from doing scalar Bernstein way back in the day when we started on an earlier slide is that you need a d in this log to get rid of this guy if you want small probabilities. Okay. So what's the takeaway? It's that you can do concentration on martingales, but you have to worry about some extra object. And for us, it's this funny notion of variance, which is called the predictable quadratic variation, and which is a random variable. So we're going to have to be a little bit careful for thinking about it. I think you can come up with other random objects to control instead of this one, and that could give you maybe a Chernoff-like version of this too. Okay, now we want to think about an application. So we're going to talk about Laplacian matrices, which are maybe not familiar to everyone here, so we'll just do a quick definition. So Laplacian matrices are matrices that we use to talk about graphs, undirected graphs. So we have graph G with vertices V and edges E, some positive edge weights. Let's say that there are n vertices and m edges. Here I've got a graph on 3 vertices. I'm going to build the Laplacian of this graph. So it's a matrix that I associate with an undirected graph to help me talk about the graph. Okay, so I'm going to build it. It's going to be an n by n matrix, so a column and a row for each vertex. And I'm going to build it by summing together little baby Laplacians, one for each edge, So now I just need to tell you how to make the baby Laplacian of an edge. So let's look at the edge between A and B and build a baby Laplacian for it. So again, it's still an n by n matrix. It only has entries in the rows and columns for A and B. And it's just a 1 on the diagonal and a -1 on the AB off diagonals. And then we scale it by whatever is the weight of the edge in the graph, which is a positive number. Then we add them together, we get the Laplacian of the graph. I have more definitions, but I don't have time for them. So there are many equivalent perspectives on Laplacians, but we'll just keep with this one. So let's build an example. It's a graph on 3 vertices. There's an edge of weight 1 between vertex 1 and vertex 2. It puts a 1 on the diagonal for 1 and 2 and a -1 on the 1, 2 off diagonals. Okay, an edge of weight 2 between vertex 1 and vertex 3. It puts a 2 on the diagonal for 1 and 3 and a -2 on the 1, 3 off diagonal. Another edge between vertex 2 and vertex 3, and adding them all together gives us the Laplacian of the graph. Okay, so theoretical computer scientists, we just love solving Laplacian linear equations because it lets us do a lot of fun algorithms. So this is a very basic building block. So it was people got very excited when Spielmann and Tang in 2004 showed that you can solve these linear equations in time that's nearly linear in the number of non-zero entries of the matrix, which is just the number of edges in the graph. So this is a very useful tool, but let's not talk about why. We just want to learn about martingales today. Then there was a lot of other work making this much more reasonable. And I'm just going to focus on one particular paper which gives a very simple algorithm for solving these linear equations, and it uses matrix martingales. Okay, so we want to solve a Laplacian linear equation. So we've got L and B, and we want to find x such that Lx equals B. Okay, the classical way to do this is Gaussian elimination, which says let's find an upper triangular matrix U such that U transpose U equals L, and then we'll set x equal to U inverse, U transpose inverse times B. Okay, but the last step is easy because we can solve linear equations in upper and lower triangular matrices very straightforwardly, okay? First you look at the row that only has 1 entry. You solve in that row. Then you look at the row that only has 2 entries, but you know the answer for one of them. You solve for that row and so on. Okay, if you didn't follow that, you can think about it offline, but it's not a terribly hard exercise. But how do we get the U transpose U? Well, we'll talk about that in a second. First, let's see what's our algorithm going to be. It's Gaussian elimination is not fast in general. It's an n³ time algorithm, but we'll make it fast by doing approximate Gaussian elimination. So we're going to find a U that's upper triangular such that U transpose U is approximately equal to the matrix L. So this is weaker than what we had before. So what are we winning? Well, we'll gain that U will be sparse, and we'll be able to compute it very quickly. Okay. And then the fact that it's only approximately a decomposition of the matrix we wanted is not going to be much of an issue. We'll do log 1 over epsilon iterations of solving linear equations in the wrong matrix, fixing the leftover error, and then when we've repeated this a few times, we get an epsilon approximate solution in some notion of approximate that I haven't told you about yet. But we'll get there. So it's not a big problem that it's only approximate. Okay, so Sushant Sachdeva and I showed that when L is a Laplacian matrix with m non-zeros, you can find in m log cubed n time an upper triangular matrix with m log cubed n non-zeros. That's a pretty good approximation in the sense that it gives a decomposition that's approximately equal to our starting matrix in a way that's sufficient for solving linear equations. Okay. Questions about that statement?
What's the approximate to spectral norm?
It's a constant factor approximation in spectral norm. It's a very, very strong statement. Okay, so let's remember how Gaussian elimination works. There's a slightly unusual perspective going on here, but if you don't see, if you don't remember the difference, it's not important. But we take an additive perspective on it. So let's take a matrix M, that's PSD. And let's do Gaussian elimination to it. Here's an example. Okay, so first we find the rank 1 matrix that agrees with M on the first row and column. So that's the first row and column. Here's the rank 1 matrix that agrees with it. Let's subtract the rank 1 matrix. Now we have 0 in the first row and column. What's left, and we say we have eliminated the first variable. What's left is a PSD matrix, and we can repeat. So we're going to find a rank 1 matrix that agrees with our matrix on the next row and column. Here it is. And we can subtract it. There's 0 in the first and second row and column. We've eliminated the second variable. And we can keep repeating this until we've written all parts of the matrix as rank 1 terms. And notice a very special structure. The second term has non-zero entries only from the second entry onwards. The third term has non-zero entries only from the third entry onwards, and so on. So we can rearrange this as the product of a lower triangular matrix and an upper triangular matrix. This is just, this column goes with this column is my first rank 1 term. This column goes, sorry, with this row. This column goes with this row is my second rank 1 term, and so on. Now if we transpose that lower triangular matrix, we see that we found our U transpose U. Okay. So that was Gaussian elimination. Now what's special about doing Gaussian elimination on Laplacians? The remaining matrix, after we pull out some rank 1 parts, is another Laplacian. Okay? So let's see an example of this. Here we have a Laplacian matrix. I'm going to write it as a rank 1 term that agrees with the first row and column, and then what's left. So here's the rank 1 term. You can see that it's rank 1 because I now write it as an outer product of a vector with itself. And then look at what's left. It's another Laplacian. You're not used yet to checking quickly whether something is a Laplacian, so maybe don't try. But it is another Laplacian. Okay. So we saw something special about Laplacians. We saw Gaussian elimination. Let's talk about why it's slow. So solving Lx equals b by Gaussian elimination can take order n cubed time, even when the matrix is a Laplacian, and even when the input matrix is sparse. Okay? And the main issue is what's called fill. So we've got our Laplacian L, and we want to eliminate a row and column v, which in the graph, we can think about the corresponding graph, it's a vertex v, and there's a bunch of, it has non-zero entries. This corresponds to edges to other vertices in the graph. So let's look at the graph picture for what Gaussian elimination does. So it says, this variable would disappear and its edges to other vertices will disappear. But then in the remaining matrix, when we look at that as a graph, we no longer have this vertex, but we have a clique on its neighbors. So this is what Gaussian elimination does. When we pull out this rank 1 term, we're going to create a clique on the neighbors. So elimination creates a clique on the neighbors of V. Okay, these cliques can very quickly make the graph grow dense, and this is what makes Gaussian elimination slow. So this happens, for example, in an expander graph. Okay. But
why don't you just do symbolic reordering, like with minimal degree or something?
That doesn't work at all. There's no ordering for an expander graph.
Okay.
It always gives n cubed. Okay. And that's not just expanders. That's not that hard to construct cases where it's like that. Okay, so, but there's hope because Laplacians are particularly susceptible to sketching, right? I would say sparsification, but we're in a room where you say sketching.
Sparsification is sketching.
Yeah.
We're okay with that.
It's a particular kind of sketching, right? So we can sparsify this clique, okay? And we can hope that the new matrix is a good approximation of the old one, right? But we're going to have to do this a lot of times, right? I probably can't apply a matrix Chernoff bound every single time I eliminate a variable. That would go wrong. But this is exactly what we're going to do. we're going to eliminate variables and just immediately, without even, in fact, we don't have to write down the clique ever. We can sample from it without writing it down. And this is going to be our algorithm for doing approximate Gaussian elimination. Now, we won't have time to go into the sampling exactly, but it's 3 lines. It's very straightforward. 3 lines of code. So Gaussian elimination said pick a vertex v to eliminate, add the clique created by eliminating v, and repeat until you're done. Approximate Gaussian elimination says pick a random vertex v to eliminate, sample the clique created by eliminating v, and repeat until you're done. And that's the whole algorithm.
So is this something done again by effective resistance type stuff?
No, you don't need to calculate anything. Yeah. And for the numerical analysis people in the audience, of whom there are many, this very much resembles doing randomized incomplete Cholesky factorization. So in a way, you can think of this as us saying, well, the algorithm actually works, and we can prove it on any Laplacian matrix, but we have to randomize it. And neither of these randomizations is an artifact. So picking a random vertex is not the only way to do well, I think. But there are orderings that will give you trouble. And random orderings work. Okay, so remember the goal was to get that, that U transpose U in the end is going to be approximately equal to L. So how are we going to prove it? Well, we're going to show that in expectation, U transpose U is indeed equal to L. And then we're going to show that it's concentrated around its expectation. And then we'll apply a concentration bound. It will be matrix Friedman to show that it's approximately equal to L with high probability in a useful spectral sense. So first, let's look at the expectation. So consider eliminating the first variable. And now I'm going to call the original Laplacian L0. And then I write it as a rank 1 term. I'm not doing any sampling yet. A rank 1 term, that's the row and column I pulled out. And then a remaining graph plus a clique created by elimination. Right? Now I sample the clique. Right? This gives me my approximate matrix after 1 elimination. Let's think, and let's call it L1. Let's think about the expectation of L1. Okay. Well, the expectation of L1, we're not sampling the rank 1 term, so we don't need to worry about that. We're not sampling the remaining graphs, so we don't need to worry about that. We can push the expectation past all those and just say, well, suppose that we get the clique right in expectation, then the whole thing adds up to the original matrix. Okay. And then the expectation of L1 is L0. So let Li be our approximation after I eliminations. Okay? If we ensure at every step that the sparsified clique in expectation is equal to the clique that Gaussian elimination would create, then we'll get that the expectation of Li is Li minus 1. Okay? And now with the way that I've defined martingales, this says that the expectation of the difference is 0, and this will be true conditional on the previous steps, right? It just has to be true locally that we're preserving the expectation of the clique. And we got a martingale. And I think also that I would like you to maybe consider whether this shouldn't be a fairly generic phenomenon, right? What I'm saying is that algorithms like to be locally sensible, right? And locally sensible is like preserving the expectation is in this particular step, right? And that's exactly what gives you a martingale property. So martingales are a very natural fit, I think, for algorithmic analysis, provided that you can find the right operator where some expectation stays the same. Although if you go read about dupe martingales, maybe you don't even really need to keep the expectation right. Although, of course, you'll need some control over the expectation. Okay, so we're running, slowly out of time. But, let's talk about the approximation a little bit. Is it this one, right? Is that what I'm going for? No. No, if I had this kind of spectral approximation, it wouldn't help me solve linear equations at all. Like, For linear equations, small eigenvalues are important because when I invert the matrix, they blow up to be large eigenvalues. And this spectral norm is just telling me that I got some large eigenvalues right. Okay? So we need something completely different. We need to measure the spectrum in a kind of relative sense, which we do by dividing everything through by L before we do approximations. Okay? But for matrices, dividing through by L means multiplying by L minus half on each side. So we transform our approximate decomposition, apply L minus half on each side. This is just for analysis, of course. Now, L becomes identity, and so we want this thing to be close to identity. And that's enough for solving linear equations. Okay. It's hard work to keep writing L minus half everywhere. So let's give it a name and call it isotropic position. I'll put things in isotropic position by calling them blue and putting a bar on them, just for those of you who might have trouble seeing the blue. The goal is now to make U transpose U in isotropic position be approximately equal to L. Okay, that's the most important thing, together with the PSD order or the Loevner order, which I'll just remind you says that if I have two symmetric matrices, A is less than B, it's a partial order on matrices. If for all x, x transpose AX is less than x transpose BX. Okay, let's have some random variables. Okay, so we're just sampling edges. The random variables look like either you scale up the edge by something to counter the fact that you only keep it by probability P, or you set it to 0. Okay? And this clearly has expectation LE. Okay? It's not exactly what's happening in the algorithm, but let's just think about flipping a coin for every edge. The real analysis is not much different. Then we have some zero mean variables. Just subtract the mean. And then we color them blue to put them in isotropic position. And now we remember the predictable quadratic variation. Right? This is the hard thing to control. Some funny object like this in order to apply Martingale concentration. So we wanted to show that this thing is usually well behaved. Okay? Now we can get a promise, it turns out, if we do our sampling sensibly, and this is subtle, but let's not worry about it right now, and it's often not the hardest part, that every sample that we make has low variance. Okay? And now I think we're almost at the last message I want to get across, which is that the variance was a matrix, right? And I told you it was a funny notion of variance. It looks like the Laplacian of the edge in isotropic position. Okay, that's a time bomb because this seems simple, but it turns out that we're very close to something very powerful now. It's somehow relating the variance of each sample back to the structure of the graph is a very powerful statement. But it's not enough because we're constantly changing the structure of the graph. And that's, I think, one of the hard things that we need to get used to for martingales. So remember that when we're doing elimination, we eliminate a vertex, we create a clique on its neighbors, right? Then we sample the clique, and I just told you that the variance that we create looks like little baby Laplacians on these edges, but in isotropic position, which was this weird normalization. Now it turns out that in the Loevner order, this matrix is less than the edges, so just the variance created here, these baby Laplacians, are less than the corresponding edges of the vertex that we eliminated. And this is actually not hard to see because you get this matrix by pulling out a PSD rank 1 term from this matrix. Okay? But now I solved the problem of the fact that we're changing the structure of the graph, because we went from having variance in the new structure to getting variance in the old structure. Now comes the other important part. I picked random vertices. But it's easy to think about what does a random vertex and then getting variance here look like. Because I'm getting variance of edges of a vertex equal to edges of a vertex. But when I sum that over random vertices, I just get the whole graph because I can pick either end of an edge. Right? There are two ways that I can get the edge. Pick one end, pick the other. And I'm averaging over all these different ways of getting the edges. So I get each edge twice, and I divide through by the number of vertices. Okay, so the whole variance adds up to the whole previous graph in isotropic position divided by the number of vertices. There are some fudging constants. But in isotropic position, the Laplacian is just identity. So the trick is that we can really understand what the predictable quadratic variation is doing so we can control the variance. Okay, and now we just sum up the variance. Let's skip this. We sum up the variance over different rounds. And we're dividing by number of vertices in each round and getting a small matrix otherwise. The first elimination, we have n vertices. So we're dividing by n. The second, we have n minus 1 vertices, and so on. So this 1 over number of vertices just gives us a log n because it adds up to a harmonic sum. Boom, right? There's not a lot of variance, is the whole story. So the whole thing works. Now, summary. Martingales are a natural fit for algorithmic analysis. Understanding the predictable quadratic variation or some other similar object maybe is key. And I really think you should be able to find other cases of this. We have some cases. So there was an online row sampling by Cohen, Musco, and Pachoki. We have this approximate Gaussian elimination that I talked about today. We've also been using it for semi-streaming graph sparsification, for solving directed Laplacians, for proving concentration bounds for negatively dependent matrix random variables. So, go home and take out your martingales and do stuff with them. Thank you.
Questions?
Yeah.
You mentioned that there are some orderings for which this doesn't work. Can you distinguish what are good elimination orderings and bad elimination orderings?
Yeah. So bad elimination ordering is like, suppose even, this is a bit silly, but suppose the graph is just a ring, or like the global structure looks like a ring, then eliminating in order around the ring is a bad idea, because you're sort of going to be accumulating variance in a bad way.
Can you generalize this to beyond the Laplacian?
Yeah. So we have some cases of this, but not a whole lot. So we can generalize it to something called connection Laplacians. We can also generalize it to directed Laplacians, which basically give you ways of basically finding any information about a random walk in a directed graph in nearly linear time. So I think that's a very cool primitive. But whether you can do it for everything, we don't know, and maybe don't think so. But that's a very big question.
I guess your sampling, it works because of the Laplacian, this is special property, right?
Yeah. So all the other cases that I mentioned, connection Laplacian and directed Laplacian, also have this property that they're a class that are closed under Gaussian elimination. So you do some Gaussian elimination, you get back another one of that class. If you find another class like that, you can probably do the same thing.
I mean, that's also true for positive definite matrices, but I mean, there's something else happening here.
Something else then goes wrong. So, and the fact that these matrices, always have a decomposition into small parts is the other.
You have to have something to sample.
Yeah.
More questions? All right, lunchtime. Let's thank Rasmus again.